Welcome to Spring LIB.
Okay, so for this problem, we want a thin film to produce black if it's illuminated with 480 nanometer light. So let's go ahead and start out by drawing a diagram. So here's our film, and then we know that the N of the film is 1.3, and our lambda is, I think, 480 nanometers. And 1.33. So if the light isn't reflected, i.e. it's you see black, no light, that means that the photons reflecting off of this interface and the photons reflecting off of this interface. Oh, let me do that in a different color. Actually, I guess I can just use blue because this should be a bluish color. So, and then there's going to be a photon coming up and reflecting again. So we have these two, and I drew them displaced, but of course they would be on top of each other, and these don't have to be at an angle. But these need to destructively interfere. So they need to have a phase difference that's an odd, so it's an odd multiple of pi. So like 1 pi, 3 pi, 5 pi. So I'm going to go ahead and write that as 2m plus 1 times pi. And then I can just say that where m equals, you can start at 0. It can go 0, 1, 2, and it can also be negative if we want. So it can be m is just all integers. And great. So that's what we want for our delta phi to be. So let's determine why there'd be a phase difference between both of these. So for the first one, it's loose. So we want to do, actually, let me rewind a little bit. So delta phi, so that's going to be the phase of photon 1 minus, and then let's call this number 1. So this one's number 1, and then this is the phase of photon number 2. So we want that to be equal to 2m plus 1 pi. Okay, now I can start getting into the specifics. So this second photon, it's kind of coming through here. It's not reflected. It's the photons that aren't reflected. They do get reflected here, but since this is air and this is not air, there in this n is less than this n, so this n is equal to 1. I'll kind of go back to black writing. There's not going to be a phase change. So the only phase that this is going to accrue, that photon 1 isn't going to accrue, is going to just be from the extra path that it's traveled here. And so in general, the phase that this is going to accrue is going to look like, so I mean, just in general, phase is for a sinusoidal wave is 2 pi x over lambda. And so and x is going to be, it's going to go through the thin film twice, so then that's going to be 2t. So this top is going to be 4 pi times t. This has a thickness of t. And then lambda is equal to, it's going to be 480. And then, of course, we have to divide by the 1.33 because it's in a thin film. So that means the wavelength is reduced. And so dividing by 1.33 means putting 1.33 here. Great. And then we need to consider the phase that the first photon might have a phase shift. And indeed it does, because it goes from a low to a high index of refraction. So that means it's going to have a phase shift of pi. And so again, we're going to set this equal to 2m plus 1 pi. And then now what we can do is just solve for t. So, so I guess I started using numbers. Yeah, that's fine. So let's go ahead and solve for that. So we can, this is a 1, we'll bring it to the other side. So it's going to be 2m plus 2. And then, yeah, and then if we just isolate this for t, we want to multiply this whole thing by 480 nanometers. And we want to divide by 1.33 times 4. And let's not forget to cancel this pi. And so now I'm going to go ahead and pause the video while I plug this into a calculator. And I guess for A, so one more thing. Before A, we want the minimum thickness. So let's set M equal to 0 because that's going to make this quantity the smallest. So I'll go ahead and write that down. M equals 0 implies that the thickness is, let's see. Oh, I can almost do that one in my head. Oh, well, yeah. Actually, would that make it small? So if M is 0, then this has a factor of 2. If M is minus 1, this becomes negative 2 plus 2, which is 0. And if M is minus 2, then that's minus 4 plus 2. Yeah, so M does have to be 0 to make this thing smallest. So let's do 2 times 480 divided by 2 times 1.33. I get 361 nanometers. Just pause the video and look at my calculations. Okay, I ended up actually revising my calculation and I got 180 nanometers. Okay, and then the next part of the question asks for other thicknesses. So really we can just keep upping M. So that was M equals 0. So let's go ahead and write that down here. So here's B, other thicknesses. We can set M equal to 1. And so that means we're going to do just double the 360. If you look at this math right here, and you get that the thickness is equal to 360 nanometers. And then do they want how many other ones do they want? 2 other possible. And we can just keep doubling it. So this M equals 2 means this is 4, 5, 6. So that's going to be times 6. Oh, not doubling it. I guess we want to triple the original because we're going from a factor of 2 to a factor of 6 here. So plugging in M equals 2, then we should get 3 times 180. What's that? 3, I think that's 480. Let me just double check. 180 times 3, 540, my bad. And this is to 2 sig figs, so you could redo the calculations with more sig figs, I think, if you want. Although, yeah, we are, I guess, given 3 sig figs, so you could go back and do that. That's the idea. And then if the thickness was much less than lambda, it would also appear black because, so this is getting a 180-degree phase shift. If this is basically accruing nothing as it goes through this film, then it's going to be 180 degrees out of phase with this reflected one because this one hasn't undergone a phase shift at all. It hasn't undergone a phase shift because of it hasn't, traversed this thickness, and it also hasn't undergone a phase shift here again because the air has a lower index of refraction than the